Hello everyone, I'm FaHo, a student coming from RFID and IoT lab at Shanghai Jiaotong University. It's an honor to be here and introduce our work, FaHo, Deep Learning Enhanced Holographic Localization for RFID tags. Recent years, the fourth industrial revolution has occurred after information technology has been integrated into manufacturing. And this progress has significantly changed the way of producing, moving, and storing products in the factory or warehouses. The cyber system can help us order products and check inventories. However, both these applications require accurate localization for the target objects. As an important building block of Internet of Things, radio frequency identification (RFID) technology has demonstrated to be a promising method for accurate indoor localization. It has tiny size, large range, low cost, and is battery-free. We can capture some key indicators of objects by simply attaching flexible tags on them. In our work, we focus on RFID, which has a higher resolution and is more sensitive to the change of the distance between the antenna and the tag. However, the ubiquitous multipath interference in a real-world scenario will introduce offsets in receive phases. To study these impacts of this interference on the phase offsets, we conduct several experiments in two different environments, a Multipath-rich environment and a clean one. In each experiment, an antenna moves along a trajectory and scans several static tags at about 50 measuring points. In this video, x-axis is the index of measuring points and y-axis is the phase offset. Each line is the offset of one tag. The top three lines represents the phase offsets collected in the Multipath-rich environment, while below ones are offsets in the clean environments. It's easy to find that there are significant differences among these phase offsets in the Multipath-rich environments. As a result, this uncertainty in the received phase value will undermine the positioning accuracy of many RFID localization models. Of course, there are many prior works trying to eliminate these challenges. For example, Holograms design a differential augmented holograms to improve the accuracy. Multipath-rich use multiple frequency data and propose multipath suppression algorithms to address these problems. And RF scanners derive the tag position by curve fitting the hyperbola pattern on the phase profiles. However, we find these works only achieve decimeter level accuracy in the two-dimensional plane based on our experiments. Before introducing our solutions, let me talk about some basic knowledge of holographic synthetic aperture radar techniques for RFID tag localization. Suppose we have a static tag and we use the antenna to integrate at different positions, so we got a phase profile. And we suppose a surveillance region. Next, we need to design a likelihood function, and this function can transform the phase profile into a holograms. And in these holograms, each pixel value represents the possibility of the corresponding position to be the true tag positions. Here is an example of holograms. In these holograms, the yellow region has a higher possibility to cover the ground truth. So we can also estimate the tag position based on this hologram. Here are two typical RFID holograms, and in each hologram, the red pentagrams represent the ground truth. We make some interesting observation based on this hologram. First, there is only one main lobe, and there are many symmetric side lobes around the main lobe. Second, the main lobe as well as the side lobes will change according to ground truth. These observations are apparent, but they also show that there are a lot of important patterns which can reveal the true tag positions. So we raise a question: can we utilize this pattern to improve the accuracy and solve the problems of multipath effects? And based on this point, we propose FaHo, which means take full advantage of holograms. It's a fine-grained RFID localization system that combines the holographic synthetic approach techniques and machine learning algorithm to locate RFID tags. In our system, we assume that line of sight signal is stronger than non-line of sight signals. There are two main components in our system. The first is hologram generation. It transforms the face profile into holograms. And next is position estimation. It analyzes the holograms and predicts the accurate coordinates for RFID tags. So let me first introduce hologram generation. Here is a typical definition of likelihood function, which has been widely used in the state-of-the-art systems. For each position in the surveillance plane, we suppose that it's a true tag position. So we can calculate the distance between the supposed position and all measuring points and get the theoretical phases easily. This function measures the difference between the measured phases and the theoretical phases of all measuring points. If suppose the position is the ground truth, although there may exist some multipath effects, this difference would close to zero or a constant, just like this, and leading to a large likelihood. Otherwise, it would output a much smaller likelihood for the fake positions. So we got this hologram. And based on this function, we propose a new hologram by adding an extra term. It calculates the cosine similarity between the measured phases and the theoretical phases. Similar to the former explanation, if the supposed tag position is the ground truth, the measured and the theoretical phase would have similar shades despite there may exist some phase offsets, resulting in a larger similarity, just like the red and the blue lines in this figure. So this function can also create larger likelihoods for the true tag position. Now the naive holograms can be transferred into a new one. And it's easy to find that in these new holograms, the resolution improved a lot. And there is also an interesting phenomenon that the main lobe is sliced into several spots. However, the former holograms only consider the performance of the supposed position. The likelihood of one position can be easily affected by the multipath effects. As we mentioned before, the tag position can affect not only the likelihood of the ground truth, but also the likelihood of other positions in the holograms. And there are many stable patterns in these holograms. For example, starting from the ground truth here, and if we move left or right, we can find the likelihood decrease quickly. But if we move up or down, the likelihood does decrease, but it decreases slowly. And this pattern of likelihood in an area is more robust compared to the likelihood of one position. So to utilize these features, we design joint holograms where each likelihood considers both the performance of the supposed position and its nearby position. The yellow region is called kernel region in our system, and it determines how many nearby positions that one likelihood should consider. Here is the definition of the likelihood function in the joint holograms. The left element is a real likelihood functions calculated by the measured phases, which contains the likelihood of the supposed position as its nearby positions. It also corresponds to a subset of an original hologram. And for each supposed position, we can also get a theoretical likelihood for its nearby position easily. So now we have two matrices here, and we add the correlation coefficient between the two matrices into the function. And if the supposed position is true, the two matrices would have similar and traits and match each other. So we can get a larger correlation coefficient, and the function would output a larger likelihood for the ground truth. Here is a joint hologram. We can find the resolution has been advanced significantly, and more importantly, the likelihood in the joint holograms are more robust, since each likelihood considers the performance of its nearby position and utilize more information in the hologram. Here is a brief comparison between the three holograms. After the several process, we can find the resolution has been improved a lot. The next component is position estimation. After generating the joint holograms, we need to estimate the tag position based on them. Previous studies selected the position with the largest likelihood as the true tag position, which is a typical largest likelihood estimation method. Here, the black square represents the ground truth, while red pentagram is the largest likelihood position. If there is no multipath effects, this method can work pretty well and accurately estimate the tag position. However, if multipath interference are strong, things go different. Based on our experiments, we find two possible effects which can remarkably undermine the performance of the largest likelihood estimation. The first impact is side lobe disturbance. If there exist strong multipath effects, several spots in the side lobes may have higher likelihood compared to the ground truth. So this method would fail in this situation. And the second impact is main lobe ambiguity. As we mentioned before, the main lobe is participant into several spots. If the multipath interference is strong, some position in other spots would also have larger likelihood. As a result, the largest likelihood estimation also creates some errors. Therefore, it might not be a good method to estimate tag position, especially in the multipath-rich environment. Fortunately, we also observe some interesting patterns at the same time. The first, the main lobe is surrounded by the symmetric side lobes and participate into 3 or more strong spots. So if we can utilize these patterns, we will recognize the main lobe correctly, so we can solve the problem of side lobe disturbance. And the second pattern is only spots second close to the synthetic aperture covers the true tag position. Here, the synthetic aperture represents the x-axis. So if we can utilize this pattern, we can also adjust the main lobe ambiguity. All these findings demonstrate that there are many useful patterns in the holograms which can be utilized to improve the accuracy of RFID localization models. So to take full advantage of this pattern, we treat holograms as image and construct convolutional neural network to learn this pattern. It's a typical CNN 3 convolution layer, 1 jump layer to avoid all fitting, 3 fully connected layer. Finally, it outputs the exact coordinates of the target tag. However, there is also a new question: how to train this neural network? We don't have any open datasets, and of course, we can conduct a large amount of experiments and collect enough data to do this. But this method the training cost of this method is too high and is also extremely time consuming. To address this problem, we choose to use simulation datasets. We add different random Gaussian noises to the measurement points to imitate the multipath effects, and this dataset is much larger and cheaper. Next, we collect a small experiment dataset to validate and select the neural network. Finally, our localization model is tested on a larger experiment dataset. We implement a prototype of FaHo using custom RFID devices and conduct lots of experiments in 2 different environments, a Multipath-low scenario and the Multipath-rich scenario. In the Multipath-rich scenario, the experiment is conduct in warehouses where exist many metal objects, which can introduce multipath effects. Besides FaHo, we also implement many state-of-the-art systems such as RFID scanner, Hologram, and Multipath-rich. We compare the accuracy of all these systems, and the CD plots of the localization error in the two directions demonstrate that our system achieve much better performance compared to the other systems in the multipath-low environment. And in the multipath-rich scenario, the result also show that FaHo outperforms other works, especially in the right directions. And more importantly, only our system achieves centimeter level accuracy in a combined direction in this scenario. We also investigate accuracy of different holograms, including naive hologram, basic hologram, and joint hologram, based on largest likelihood estimation. It's easy to find that joint holograms obtain lower localization errors compared to other holograms. And the result also prove that we can improve the accuracy by considering the likelihood of nearby positions and by utilizing the stable patterns in the hologram. Next, we evaluated the performance of kernel region with different size. Here is the localization errors of different kernel region in two scenarios. We find too large or too small kernel region would undermine the accuracy, so we use the validation dataset to select the best fit kernel region for different environments. We also compare the performance of our convolutional neural network solution with a traditional largest likelihood estimation solution. We conducted a series of experiments by combining different methods. We compare their accuracy using different holograms in different directions and different environments. The results are somehow complicated, so you can refer our paper to see more details. In conclusion, the convolutional neural network solution significantly outperforms the largest likelihood estimation, especially in the y directions based on our experiments. And last, we evaluate our system in two application scenarios, ordering and reconstruction. We compare the ordering accuracy of FaHo with other works on the different text spacing, and our system achieves better performance in all cases. We also design a simple method to recognize the placement of the target objects. In these experiments, each box is attached to text, and FaHo estimates the accurate coordinates of them. Next, we use the position relationship between the two texts to determine the placement. The results show that FaHo can achieve an average accuracy of 90%. And our work also has some limitations. First is environment dependence. Since we use a validation dataset to determine the final localization models, our system is environment dependent to some extent, which means if the environment changes, our accuracy may decrease accordingly. And the second is deep learning. This is because we adopt deep learning algorithms, so we are not pretty sure about how the convolutional neural network process the hologram and how they learn these patterns. But I think in this work we make a good investigation on an important idea. In the traditional localization models, they sometimes have many useful and important patterns. And existing studies do not use this pattern, or traditional algorithms fail to utilize this pattern. So how about use deep learning algorithms to take full advantage of this pattern? And in return, it can also improve the accuracy or the performance of a traditional localization model. And I also believe that these ideas can apply to other localization for other devices such as Wi-Fi. And here is the conclusion. We propose a fine-grained RFID-based localization systems, and which utilize deep learning enhanced holography techniques to locate RFID text we designed new hologram called the joint hologram, and we utilize deep learning algorithm to locate text and implement a prototype of FaHo and evaluate its performance using many experiments. And in the end, let me use this chance to make a little advertisement for myself. I'm FaHo, final year master student in software engineering at Shanghai University. I received my bachelor degrees at Nanjing University. My research interests lies on ubiquitous computing, mobile computing, especially in the related field of wireless sensing. And currently I'm looking for a PhD opportunity. And I published 3 papers as the first author and a paper as the co-author. They are accepted by SenSys. You become second and MS wing. And I'm always eager to improve myself. And if you are interested in me, drop an email to me or talk to me directly. Thank you, that's all.